So, who is very knowledgeable of the maths of neural networks. And so here's the idea. The idea is we're going to, I'm going to give you an intuition, like the aha moment, okay? But brief about me, I run Data Weekends. My name is Francesco, by the way. I run Data Weekends. It's a program where you have 2 to 5 days workshops about analytics, machine learning, deep learning, and so on. I also run a company called Catalyst, and with that, we serve a bunch of companies for trainings in the same kind of stuff. And recently, I published a book called Zero to Deep Learning, which is basically meant to bring you from zero to deep learning. Okay. So basically, long story short, I train and the company trains engineers. And this is for today's talk. It's like, I want to give you the aha moments. Get an intuition of how the maths behind neural networks work. And here's the joke. What I'm trying to do is really simple. Shouldn't be that hard. And the guy says, oh, computer, just carefully organize and everything is hard until someone makes it easy. And then maybe I should turn this back. Sometimes we are really frustrated with technology. It seems so complicated. And can we make it simple? Can we understand it at a simple level? Let me just do one quick thing here, which is use a separate displays here. Cool. All right. So 3 things I'm going to cover: cost function, stochastic gradient descent, and backprop. Okay? So let's talk about cost functions. Raise your hand if you think you have a fair understanding of what a cost function is and what the purpose of a cost function is. I'd say about half the people. Okay. So raise your hand if you're familiar with linear regression and you know linear regression from high school. Great. So let's start with that, and let's talk about cost function in a case that is familiar for everybody. So here I have a very simple case of linear regression where I have an input data, size of houses, and output data is the price of such house. And I want to build a linear regression that basically takes the size of the house and predicts the price. So what I'm really asking is, can you find a function, okay, that given the size and input returns the price in output, okay? And if this was not a linear regression, but it was a neural net, the neural net would be here. Nothing changes. The framework is the same. Features input, labels output, okay? So what we are doing when we decide to use a model, we are formulating what's called the hypothesis. Okay, so we're saying the relationship between our inputs and our outputs is a line, is linear. And in this case, linear regression, we only have 2 parameters, where we cross the vertical axis and the slope of the line. So basically, B and W, and oh look, it's bias and weights like in neural nets. So B and W are the 2 only parameters that basically will decide which line we will choose. Okay. So what I've done here, I've mapped a machine learning problem, okay, into an optimization problem, find the 2 best parameters to basically solve that problem. Okay, 2 optimal values of B and W. Okay, so how do we do this? Cost function. That's what we need to basically make a choice between a line like this, a line like this, a line like this, a line like this. What do you think a good cost function for the case of linear regression is? How can I define a cost that is basically high if I am doing a wrong thing and low if I'm doing the right thing? What could be a cost? Mean squared error. Any other suggestion? I could also use mean absolute error. So long story short, what I want to do is measure the error between my line and my data. and somehow average overall my data. So I could do the mean of the absolute distances, the mean of the square distances, the mean squared error is the mean of the squared of the distances. Several options are possible. The point is, I've now told what penalty is associated with any choice of parameter. If I choose a certain value of b and w, I will have a cost. So the intuition, the aha, is this. Let's say I chose this line, which has w equal to 0, because it's flat, and b equal to some value 110. What I'm going to do then is calculate the error, okay? Which these are called, technically these are called residuals, but that's not important. I calculate the error, and then I calculate the squares, average out, I get a certain value for the cost. Now let's say I'm curious to see what happens if I change W. Okay, so if I change the slope of the line. What I can do is change that slope. This will change the value of the residuals, and the overall error will be smaller. Okay? And now I can do it again, and the overall error will also be even smaller. Okay? Until at some point, oops, now the error is bigger. The cost is bigger. So my optimal line in this very simple case is found by a parameter value that's somewhere here, between this value and this value. In a way, what I'm doing is I'm sampling my cost surface as a function of one particular parameter, the one that controls the slope of the line, looking for the optimal value of that parameter. Yeah? Cool. If I have more parameters, in the case of b and w, instead of having just a parabola, I have a funnel, but that doesn't change very much. And so basically that's the role of the cost function. Okay? It's driving my choice of the parameters. Okay? Yes? How do you choose the right cost function? Very good question. So you choose the cost function based on the problem you want to solve. So for regression, in general, not just linear regression, mean squared error is a good cost function. For classification, for example, mean squared error is not a good cost function. What you're going to use is something called cross entropy or log loss, which is well defined for binary labels or for categorical labels. Okay, so depending on the type of labels you have, you will choose a certain cost function. In fact, there are many different types of cost functions. The good news for you is that you probably don't have to guess because someone in the literature has solved that problem for you. You just need to look like cost function for classification, and it will tell you use cross entropy. Okay, very good question. Any other questions? Yeah.
So along that line, do you mock up to that portion of error and
can you repeat?
You take into consideration errors that are both fixed values, the most proportional value that you have.
I'm not exactly sure what you mean.
So the error function that after the y plus an error plus error 1, error 2.
Okay, so errors that are also proportional to the value.
That's absolute error.
No, usually you take values that are absolute. Okay. So that's cost function. Now, to extend to neural net, the only difference is we don't have 2 parameters. We have many more. And so let's talk about gradient descent. How do we navigate this cost surface to reduce our parameters. What's the rule? The rule is the following. Let's say we have one parameter, okay, a certain weight in the network, and we do all the things we've said, like forward propagation, etc. We see that. Basically, we get to a certain value for the cost. Okay? Now, the problem is we don't know the cost function. Okay? We only know the value of the cost for this particular value of the weights. So we don't know that the cost function is like this and that we should be going this way. So how do we minimize the cost if we don't know it, except for that particular value of the parameters that we're using? And if you think of how you do it with neural nets, usually you initialize the neural network with random values for the weights. Okay? And so basically this is one weight in the millions of weights that are there in the network, and it's a random value. So that and all the others, they give us a certain cost over the batch or over a certain number of data points, but we don't know the rest of the cost surface. Okay? So how do we do it? Any idea? It's in the title. We look for what's called the gradient, which is a magic word to say the slope. Okay? So there is some mathematical technique called the derivative of calculus, okay, which given the value of the weight here, and since we know the function that the network is doing, also allows us to calculate the local slope of the cost with respect to that particular parameter. What does it mean? It means that for a little change in the value of the weight, we can know if the cost is going to decrease or to increase. Okay? So now we not only know the value of the cost, we also know the local gradient, the local direction of descent. Okay? And so we do the simplest thing possible. We do one step in the direction of the gradient. SGD, stochastic gradient descent, I call it simply go down. Okay, do one step in the direction of going down. Okay, so this is the rule. I take the weight and I update the new value of the weight with the old value minus, this is fancy math to say the gradient, okay, the slope at that time. Does this work? Well, let's see. Let's say I'm here. So the gradient, this derivative, for those of you who know math, this derivative, is it positive or negative? In this particular case, where the slope is negative, right? It's pointing down, okay? So this term here, this fancy thing here, is a negative number, less than 0. Okay? So W minus a negative number is equal to W plus a positive number. Okay? So it's going to take W and move it to the right, which is exactly what I wanted. So it's going to move it to the right. What if I were here instead? I don't know the cost function. I know just the value of the cost, which, by the way, is the same cost as before. Okay? But the gradient is positive. Yeah? So I take W and I subtract a positive quantity. Guess what? It makes W move backwards, move towards negative values. Okay? So this very simple rule is all I need to do the gradient descent. Okay? So I start with a random value for the weight. I calculate the cost. I calculate gradient, and then I update the weights using the gradient. Yeah.
So this is two-dimensional. So this is, but when we start getting into multiple dimensions,
when you start getting multiple dimensions, this is the mess you're faced with, right? So think as if you are on top of a mountain and you have to go down, and you actually, it's very foggy. So usually what I say is like, you're on Twin Peaks, you have to go down to Great Valley, but it's a complete fog, right? And so what you do is you poke the direction, that's what you're doing with the batch, and take the gradient gives you the direction of steepest descent even in multiple dimensions. So the gradient is a vector of derivatives, which is the derivative of the cost with respect to all the parameters. So you update each parameter with the partial derivative of the cost with respect to its itself. So this formula is still okay. Now there is an additional problem, which is you cannot simply just go down, hopping down and stopping at the minimum, because, for example, if you started here, you would end up in a local minimum. Actually, that's what happens all the time, and that's why a lot of research went into these fancy names like SGD, Momentum, NAG, Adagrada, Delta, and RMS-Prop, and other. Those are optimization algorithms that take the simple stochastic gradient descent, SGD, and improve it in one way or another so that you don't get trapped in these local minima. Not going to go over the equations for this, but basically each of them is SGD on steroids. What I can do is give you some intuition on how they work. For example, so SGD is this red guy that slowly but surely gets to the goal. What do you think the green guy is doing? The green guy is momentum. Observe what's happening here, and let me guess what's going on.
The steepest.
It Yes, it's going the steepest. It starts off the same direction as the red, right? But instead of turning here, it keeps going. So the analogy I usually find to describe this is you're again on top of Twin Peaks, but instead of walking down one step and then reassessing your scope, and then walking down another step and reassessing the gradient, and then another step, which is good. You're now on a bike. So you're going down, and oh, okay, I have to turn, but I'm still going this way. So I have momentum. And I start turning, but I kind of keep going a little bit in the direction I was ready for. On a bicycle. Okay. So that's what momentum does. It saves us from getting stuck in local minima by adding some momentum, like the name says, like some speed, where I keep going in the old direction and then I start steering in the new direction. Okay? And then the other, like Adagrada, the Delta, and RMS-Prop, they're variations of that, where I kind of average out the behavior with some damping and some smart or not so smart math, so that I don't have these oscillations any longer. Yeah. Right.
So in that case, I think momentum on getting something. But if you push, get much closer to possibility.
Yeah, basically they allow you to explore the surface because you have so many parameters. Your surface is very rugged, and so you need to find that big funnel where you end up. Yeah. Yes. Yes. General rules, RMS prop and Adam work really well in most practical cases. If you're fine-tuning something with very, very tiny learning rate, SGD is also a choice. And then, you know, new algorithms come out as well. Yeah.
Now, say vein, some of these have really fast, but maybe one that's stochastic gradient descent. It might be more honest to call it batch average gradient descent. By understanding how it works, right? I actually blew an interview question because I was asked to describe stochastic gradient descent. And I'm sure you guys know what the stochastic process is, but it has very little to do with that. And today was something really simple. All right, so in that vein, you have a like one paragraph description on your website. Every one of those, make it a little movie like you have.
I don't in the website, but in the book, yes. And I can point you, if you don't want to buy my book, I can point you to free resources where that explanation exists. So yeah, there is not so difficult. If you actually take half an hour to read through the algorithms, they're essentially variations of smoothing applied to stochastic gradient. Yeah. Okay. So, how do you guys feel about a bit more maths? Talking about backprop. Yeah? I know Chris told me don't do backprop. So I just want to give you a couple of pointers and then show you a snippet of code that I hope will be helpful to clarify how backprop works. So let's recap. We've defined the cost function. Okay. The cost is this one. Where is it? Oh, come on. So we've defined a cost function. Okay. And we've defined and we've defined how to navigate the cost surface using an optimizer. Okay? Now, the one missing piece is how do we actually calculate this derivative? That's the only thing I've not told you. I've taken it for granted that we can calculate that gradient, and then everything else follows. So that's the missing link. Let's do that, and then we're done. Okay, so this is a simple unidimensional two-layer neural net. Okay, let's see, why do I say that? Well, it has the features in input, just a number. It's multiplied with the weight. Then it's added to a bias. And I'm showing what would look like the TensorFlow graph. Okay, so every operation is a node in the graph. And then I call this intermediate result Z. I apply an activation function. This is A. Then I multiply A with the new weight for the inner layer. Add a new bias, that's Z2. Again, a sigmoid, that's my output. And the output gets combined with the label to produce a cost. So I have all the operations from the beginning to the end. What are my inputs? My inputs are X and Y, the label. What are my weights and biases? W2, B2, W1, and B1. So basically, when I calculate the gradients, I need to calculate the derivative of J with respect to 1, 2, 3, 4 parameters. And then each of these weights and biases gets updated with its own derivative. Okay? So, yeah. Sorry, say again? You want to calculate how the bees these are parameters in the network too, so you need to calculate the gradient with respect to B as well. Well, it's linear if this were a linear regression, but you have these non-linearities, and so you have non-linear dependencies with respect to B as well. Yeah. Okay, so this is the forward pass. Let's read through it. Z1, I'm just rewriting as equations the same graph, no magic, okay? Z1 is X times W1 plus the bias, so linear combination, followed by the sigmoid applied to Z1. This gives me the first activation. Then I take this and plug it in a linear node again. This gives me Z2. Sigmoid again. That's A2, which is also my output, so these are identical. And then I have my cost, which I have not defined here, but if this was a linear regression, that this was a regression to the mean squared error. If it's a classification, this would be log loss. Whatever your cost is. It's a well-defined function of your predictions and your labels. Okay? So let's do backprop. What we want to calculate, let's say we want to calculate, I'll do it for one weight and then it's the same forever. Okay? So let's say we want to calculate the derivative of J with respect to W2. Okay? How do we do that? There is a thing that comes from calculus. It's called the chain rule, which is this very ugly thing. But let's break it down. The derivative of J with respect to W2 is what? The derivative of J with respect to Y hat times the derivative of Y hat with respect to Z2, which is under here, times the derivative of Z2 with respect to W2. So basically, since these are nested functions, I'm applying the chain rule and deriving differentiating each of these with respect to its own argument and multiplying it with the next derivative. Okay? So I'll use a notation here, which is the following. The over line here, the big line, means the derivative of the cost function with respect to whatever is here. It's just a notation I'm introducing, okay? And this is going to be a number. It's evaluated. So whenever you see something with the overline, it means I've calculated the derivative, plugged in all the weights. This is a number, okay? And so I can rewrite this ugly formula as overline of W2 equals to overline of Z2, which is basically this whole thing, times the derivative of Z2 W2, or overline of Y times this other. Just notation changes. But now the magic happens. Why? Because I look at this and say, okay, let's calculate this one first. Well, this one is well defined. Okay, so step one, I calculate the derivative of J with respect to Y hat. And it's well defined because if this is mean squared error, I can always calculate the derivative of mean squared error. If this is log loss, I can calculate the derivative of log loss. So basically, Y hat overline is a number. 3, 5, 0.2, whatever, it's a number. I calculate it, I forget about this derivative, I will never have to calculate it again. Why? Because now, the step 2 is I want to calculate this Z2 overline, which is the derivative of J with respect to Z2. And guess what? If I look at the formula, Z2 overline is Y hat overline times the derivative of Y hat with respect to Z2. Why? Because I'm looking here and the derivative of J with respect to Z2 is the derivative of J with respect to Y hat, which is Y hat overline, times the derivative of this guy with respect to this guy. So I'm propagating back what I've already calculated. This I don't calculate any longer. This is there already. I've done it in the previous step. And now I use this to plug it in this formula. Only thing I need to calculate is the derivative of this term, which is the derivative of the sigmoid function with respect to its own argument. Okay, and I multiply the two. Then I calculate this becomes a number. I will never have to recalculate it. Because the next step, which is what I was interested in, is W2 over line. And this is this number, which I've just calculated, times the new derivative that I have to calculate. Okay? And this I calculate again from these formulas. Z2 derivative with respect to W2 is A1. Okay? So basically, it's called backpropagation because I can plug in whatever derivatives I've already calculated as numbers and calculate the new contribution to the weight going backwards in the network. Then I have all of the corrections. I can update the network and move on to the next iteration of the stochastic limits. So basically, and so on. Okay? I know this may seem complicated, so I have a little snippet here of code that I want to share. Huh?
Yeah, recording is gonna die if I. Oh, dude, yeah, okay, 96.
Yeah. What? I was not planning to, but yeah, we can talk about this. I'll ask if there's any questions. Okay, so I'm loading here a little data set. I'm sure you're all familiar with it. It's the Titanic data from Kaggle, creating a few features. So taking some dummy fields for the class, the environment port, and the specs, and dropping a few other fields. Basically, I end up with two variables. X are my features. I have 891 data points, each with 6 features. Y are my labels. Those are survived or not survived, 0, 1. Okay? Then I define a neural network by hand. No TensorFlow, no Keras, no nothing. Just NumPy. Okay? So here's how I do it. I say my model, remember, it's just the weights. Okay? So I have random weights with the input, with the shape input dimension, hidden dimension. That's the first weight matrix. And the second is hidden dimension, output dimension. Okay? These are my weights. I have the sigmoid function, which is 1 over 1 plus the exponential of minus x. Or I have the derivative of that, okay, if derived as a flag. I have the log loss, which is defined here. And then here's the model. Notice that I'm also setting the biases to 0 and not using biases in this particular version. So run, okay, does the forward propagation. Takes the layer 0, which is the input, does a matrix multiplication with the weights of the first layer, applies the sigmoid, this is layer 1, and then repeat that, and that's layer 2. And I return both of them. And then the training step is first I run the forward prop, and then I run back propagation, which is exactly what I've shown you in formulas. I calculate the derivative of the cost of the log loss with respect to y hat. Then I multiply this with the derivative of the sigmoid, with the right equal true. And then I calculate that, and I multiply that with the weights, and I keep going back. I never recalculate any of these terms. See, L2 gets here, then L delta, L2 delta gets here, and I keep updating one step backward until I've calculated all the corrections. And then I update the weights. This is just for displaying the loss at the end, but the weight update is this rule, where I do the weight 1 minus equal to learning rate times layer 1 dot L2 delta and learning rate times X dot L1 delta. Okay? If I run this, the loss goes to 0 very quickly. So basically, the network has learned this very simple data set. Okay? This is all I have to show for tonight. Happy to answer if you have any question. Let me go back to the presentation. So this was the code. The code, you can find it in this 7 days free deep learning course that's on the zero2deeplearning.com website. So just put your email and you can download both the code and the explanation of what I've explained tonight. If you have questions, feel free to reach out directly to me in any of these things. And if you have questions now, I'm happy to chat about them. Yeah. Yes, it could be something that is not sigmoid. It could be ReLU or TANH or different nonlinearity. But you always need to have one operation like linear and then nonlinear function. This is true for fully connected networks. If you have a convolutional or recurrent, it's a different story. Yeah. Yes. No, you want the architecture to be completely differentiable end to end, otherwise it doesn't work. Yes. You can have pointwise discontinuity in the second order derivative, but you want for example, ReLU, okay, is a pointwise linear function, but that still works. But you don't want non-differentiable functions. Yeah.
Does your book cover more than what you thought?
Say again?
Your book, does it cover more than what you thought right now?
Yeah, the book goes over convolutions and recurrent and text processing and the whole thing.
The derivative function that you implement using NumPy, maybe it assumes x is less than 1.
No.
X is x 1 minus x. That is your derivative. So that means I'm assuming x is less than 1.
Why?
Otherwise,
And what?
derivative is b. Every time is b. And
The derivative with respect to its own argument. So the argument will be negative positive.
So the whole purpose would be like having that nonlinearity so that you can do the differentiation.
No, the whole purpose of having the nonlinearity is because if you didn't have that, multiple layers still produce a linear combination of the inputs. So basically having a deep network would give you any power. Putting a nonlinear function between two linear combinations gives you deformation of your features and new combination of the features that are not just linear combinations. If you don't put that, you can have 1,000 layers, just a linear combination of these. Doesn't have any power.
So from the pi standpoint, like the reason why ReLU is popular, from my understanding, is that that's much.
The calculation is very much simpler. It's a if statement. If it's bigger than 0, then x is lower than 0, then 0. Whereas TANH or the others, they involve many more calculations.
And then the other part, for the chain rule, you're storing, but there's millions of these like connections, millions of different how do you
store them in a gradient matrix, and that's why you kind of background. You're doing, instead of having products that multiply back, have matrix multiplication that propagate back.
And they're being stored in the GPU RAMs.
Yeah, the GPU is taking care of that.
You're using Relo. I mean, Relo is not differentiable zero, right?
At zero.
So they say in the Wikipedia article that they use a range. They call the tangents at zero, and then all the different slopes and tangents at zero that are so long. The plot is the range that they're using. I mean, in the engine, it's a value, right?
Yeah, well, what you can do is you either smooth Relo and say there's a smooth version of Relo which is smooth near zero. Or you take the value of the derivative. You can define the derivative of Relo at zero be 1.
Just
So you will have a discontinuous derivative, but the derivative is
that's arbitrary, right?
yeah, you would have 0 or 1.
Do you know what's TensorFlow is using? Like,
I don't know what that is. I trust it. Yeah. That's a question that I get quite often, which I rephrase as how do you choose the number of layers? And the answer I give is usually some researcher has already tried the problem I'm trying to solve for this, and so I'll just look in the literature of what of layers used for that particular problem. The other thing is, in general, what's the intuition? The intuition is the lower number of layers, the simpler the network, usually faster it converges, but less powerful. The bigger the number of layers, the more powerful the network is, the more nuanced it can be in terms of predictions, but also the more likely it is to overfit. And so you can either start with a small network and if it doesn't work, add layers, or start with a big network and if it overfits, start adding like dropout or other regularization techniques that keep overfitting.
So that would be that low regularization that would create some kind of cost function of that, or like balance overfitting versus lower accuracy.
Yes. And in general, the number of layers is a hyperparameter that you tune using something like pipeline that has multiple attempts, and you try to make the 5, 10, layer network with one attempt.
So there's a number of layers and then there's batch size, right? And the NIPS, like back in December, the magic number seems to be 8192. This is the new magic number every single time. And so what's the intuition there? The smaller batch size.
So there is an article that came out in December or November last year that basically argues that scheduling a batch size increase is equivalent to scheduling a learning rate. So the intuition there is you want to start with either a high learning rate or a small batch size because you want to jump around pretty much everywhere on the cost surface, almost random, in order to sample it here and there, looking for that big value. And then as you go on with the training, you either decrease your learning rate or you increase your batch size so that you get more stable in your update. Okay. The problem with the learning rate, you can decrease indefinitely. The batch size, you're limited by the GPU RAM. So 8192 is probably the maximum batch size allowed by current GPUs that there is standard case.
So the larger the batch size, the more data you have.
In a batch, what that gives you, it's good in that it gives you a more precise determination of the gradient, because that derivative is averaged over the batch. Like for every data point, you calculate that derivative, and then you average over 8,000.
Is extreme if you load in all of the data. That's the best case scenario.
Yes, but then you're doing one wake-up date for the whole thing. So basically, one epoch is one wake-up date. That's not all.
Getting different respect to TensorFlow. How do you differentiate an open minimum versus a global minimum?
So you're never sure you hit the global minimum. One thing I've heard from a guy that knows advanced management that I do is every model is wrong, and you are just basically looking for a model that is good enough for it. So you're basically pretty much searching to be in the global minimum. The point is that global minimum good enough for what you're trying to do? And by good enough, it means it has good performance, but also it's stable enough.
So last problem is all the data in, right? Average grade is better. Average grade is better.
Yeah.
But taking other sizes, that's all the data. Surprise and lots of small batches.
Yeah.
Lots of small batches. What does that mean?
That finds you that in one epoch, so if looking at the data once, you're actually doing a lot of wake-up dates. So think of it this way. If you take a batch that is as big as your whole data set, you're basically taking a very, very accurate estimation of that gradient direction, but you're basically doing one wake-up date, size of which is still the same. If you do many little batches, maybe you're not precise in your steps, so you're proceeding like a drunk guy going down. But in one epoch, which means one iteration over the data set, you've got a lot of steps, so that probably brought you further down. Yeah, so what the point is, if you get to too little batches, you're probably jumping around too wide. If you get a too big a batch, you're going too slow. And so there's a sweet spot of a batch size that is big enough to go fast, but small enough to go fast, but big enough to go precise.
On this batch and everything. So maybe this thing a lot of courses about like sampling, memories, like because I mean it seems like it has to do a lot with how you do sampling. Yeah. And you pull dataset to determine.
Yeah, so usually you take a random batch.
Yeah. So is there like
the question is this related to how you sample the data in your data set? Yeah, the batches are random samples of the data.
And sometimes when you know a little more about the sample, you do like there is like an advanced theories for your samples.
Yeah, I don't know if anyone has tried to apply that.
So the second thing is like about like how do you measure both? There's a measure for like how stable is your, let's say you have a classification problem, you have two classes, and you have one class you want to measure how stable is this outcome, right? So if I have like a kind of like a tolerance, like I know a little on my how strong is my, let's say my conclusion that this class 1 step class 2. So is there a measure of tolerance like classic stability tolerance more than size? You can measure like okay.
The transfer function.
Yeah, transfer function.
Yeah. So basically, the backprop is the transfer function. So you know what the dependency of the output of the process is going to be, or the output is going to be, with the change in the and calculate the derivative of the output because it's differential, right? And you can calculate the derivative respect to the input of the output. And that tells you, like, for a tiny change in any feature, that produces a certain change in the output. Right? So you end up, if you wanted to, you end up with this matrix that tells you, like, hey, for a tiny change of this, you get that much change. Or you can do it empirically, like if you change the alter your bit and how the output change. In fact, it's very interesting with images. People have these adversarial cases that fool the network, and it's a tiny perturbation of the input that basically destroys the prediction. So the meetup is called adversarial examples, adversarial attacks. Yes, there are ways to judge this.
So batch normalization comes up quite a bit, and it puts the intuition that there's a batch renormalization.
Okay, batch renorm, I don't know. Batch norm is the idea is you want to normalize your batch with respect to its own mean and standard deviation. So that you're basically just judging the differences within the batch and training the network to recognize the differences within the batch and not being sensitive from one batch to another batch. Because if the batches are small, they will be biased. One batch may be biased in one direction, and another batch may be biased in another direction. So basically, you're removing the bias from each batch, and you're just judging the intra-batch differences and training the network on that.
Oh, yeah. See, I thought it was like based on prior batches. There's like a moving average.
There's also moving average that is based on prior batches, and that's like learned over time.
And you're subtracting that.
You're subtracting the batch average and add back the moving average.
And then, yeah, the renorm it's literally renorm equals true. It's like the exact same.
Yeah, but I don't know what the formula is. Right. Truth is, there's like million pages. What do you do with it?
It's adjusted, yeah, so TensorFlow, like specifically, there's like one line, like one small documentation. It will actually boost the, oh, shit.
That drop out.
Yeah. Yeah, it's like permanent. Yeah. In fact, that's one of those optimization steps is using.
Yeah, batch same as step size. No. So, okay, I'm not sure what you mean by step size, but I'll tell you what. Okay, so that's the learning rate. Okay, yes. The batch is how many points, how many data points and labels you take to calculate that derivative. Okay, because you average over that batch. Okay. So let's say practical case. Let's say you have 1,000 data points total, and you have a batch size of 10. That means you will take the first random 10, calculate your weight of days, do one weight of days. Then take another 10 and do another more update. And so on. So you do 100 updates in one call.
Batches are like,
Huh?
batches are like,
Yeah, it's like something also data. Okay.
batch, each cycle in the batch space in one direction. That is large, that they have not like one. So it's a data problem, right? The batch size is a data problem. The batch size is 128 and 128. You're extended the average.
No, you have
128 parameter data.
you average the amount.
So if your batch becomes too large, you have to over that. You know, even increasing batch size because you have another. Why? So you have to take less than
In the beginning, yes. When you're already more than 100, you actually want that. Because in the beginning, since your weights are random, you will basically average out noise and everything. Cool. Last question.
Concept of convergence comes up quite a bit. Like, what's the intuition there? So,
As the network converge.
like, when would you want to keep an eye, or like, when would you be extra cautious? Not. So, if you have super small batches, and someone asked recently about the quantization and that potentially lead to non-convergence.
Non-convergence, your loss is unstable or something. And usually that happens either because learning rate is too high, or because the batch size is small, or because there is some other.
It also depends on what is your conversions.
So now,
Big model questions. What is the conversion criteria?
yeah, and that depends on the problem. That's usually something you find. Like, if your conversion criteria is something like your loss is lower than X, is in front when you pause and you're done. Like, what is your accuracy higher than a certain amount? And, like,
It comes down and bounces around the very end.
yeah.
Okay, right. And when do you say, oh, I don't care about this method of bounce?
Well, let's say it's bouncing around, but the accuracy is 99% on a problem that I started with an accuracy of 70%. Maybe I'm happy with, even if the accuracy is fluctuating 99, 98, or in the same depends on what I try. If it's bouncing around means I may hit or miss a pedestrian in the street, then I don't want to miss it. It always depends on what the outcome of your algorithm. Okay, no more questions.